Hello everyone, my name is Quentin Remy from Institut Jean Lamour in France, and I will present you the ultra-fast magnetization reversal of metallic ferromagnets using a single pulse of light. So first I will quickly review magnetization dynamics, then how we can achieve this ultra-fast switching of ferromagnets. This is done thanks to spin currents, which can be tuned as I will show. And finally, I will show the dynamics of this magnetization reversal. So the standard point of view for magnetization dynamics is given by the Landau-Lifshitz-Gilbert equation, where you have a precession term, damping, and inertial term, which is presented in another term. And you can also have other possible torques that act on the magnetization. But the point is that this works when the amplitude of the magnetization is constant. When one goes ultra fast, so typically below the picosecond time scale, we use ultra short stimuli to bring the system out of equilibrium, and this has the well-known consequence to reduce the amplitude of the magnetization within a few hundreds of femtoseconds. And in this case, a single equation is not sufficient to describe the magnetization dynamics. One needs to consider the full exchange of energy and angular momentum in the complete system, which includes d or f electrons, conduction electrons, the lattice, and possibly the electromagnetic field. So for ferromagnets, we can only have a reduction of the amplitude of the magnetization. But if we work with ferrimagnets with two magnetic sublattices, it is possible to exchange angular momentum from one sublattice to the other. And in the case of gadolinium iron cobalt, it has been shown that this leads to ultra-fast reversal of the magnetization. And both magnetic sublattices reverse their magnetization in a picosecond or less. This process only requires ultra-fast heating. The light itself is not required. And it is also important to note that there is no precession involved in this process. So usually in these samples, to understand these dynamics, it is possible to only consider the F and D electrons. But actually, the conduction electrons also play a very important role, because if you put a non-magnetic layer next to this ferrimagnet, it has been shown that you measure a magnetic signal here, because you actually inject angular momentum into this layer. And in the case of gadolinium iron cobalt measured by Choi and Min, it is important to realize that as one increases the amount of gadolinium in the ferrimagnet, the signal here is increasing. And so this signal is basically spin polarization of the conduction electrons, but more often we talk about spin accumulation, which is the difference between the chemical potential for up and down spins. And it can be shown that this spin accumulation is proportional to the time derivative of the magnetization. So for instance, for this magnetization dynamics, if I take the time derivative of it, this is what I obtain, which is rather close to the experimental results here. And there are two features to this signal. So first, you have a first peak, which corresponds to the ultra-fast demagnetization of the iron cobalt, and another peak, which is due to the ultra-fast demagnetization of the gadolinium sublattice. So because this peak is much bigger, we usually say that upon a femtosecond laser irradiation, it's the gadolinium that will polarize the conduction electrons. And so then if one puts a ferromagnetic layer here, such as a cobalt platinum multilayer, it could be hoped that we could transfer the angular momentum from this gadolinium sublattice to the cobalt platinum magnetization, such that we could reverse the magnetization of the cobalt platinum. And the reversal would happen only when the gadolinium sublattice and the cobalt platinum magnetization are antiparallel. And so this is what I will present here. So first I will show static measurements. So we have the sample here, and we send laser pulses from the left side, and we perform Kerr microscopy from the right side. So on one side, as I said, so we perform a Kerr microscopy, and so at first the sample is saturated. So this is what we observe. So basically there's nothing because the magnetization is the same everywhere. Then we send a laser pulse, and we see that we reverse the magnetic domain. And so the laser pulse was sent on the other side of the sample. And in this presentation, I always show the subtraction of these two images to get rid of everything that is not magnetic. And red means the magnetization pointing up, and blue means the magnetization pointing down. And because here I work with bilayers, I can also have other colors in between in general. So for this spin bulb, if I start with the gadolinium magnetization pointing down and the cobalt platinum multilayer magnetization pointing up, and I send a laser pulse, this is what I observe. So I have this magnetic pattern where on the outer region, I only reverse the magnetization of the gadolinium iron cobalt, but in the center where the intensity of the light is higher, I also manage to reverse the magnetization of the cobalt platinum. And if I send another pulse, everything reverses back. Now, if I start with the cobalt platinum and gadolinium magnetization parallel, I see that after the first pulse, no matter what the intensity of the light is, I only reverse the magnetization of the gadolinium iron cobalt. I need a second pulse to reverse the magnetization of the cobalt platinum. So indeed, the magnetization of the gadolinium and the cobalt platinum need to be antiparallel. This shows that there is a transfer of angular momentum between both layers that allows this reversal. And so the spin accumulation generated in the gadolinium iron cobalt will in turn generate a spin current, which is then reversing the magnetization of the cobalt platinum. And so now we'll show how we can control this spin current, because the spin accumulation generated in the gadolinium iron cobalt is given by dm over dt. So if I change dm over dt, I will change the spin current. And so one way to do this is to slow down the magnetization dynamics of the gadolinium iron cobalt. And an easy way to do this is to increase the laser pulse duration. So this is what I have done here. So in this outer region, at a low pulse duration, I reverse the gadolinium iron cobalt, and in the center here, I reverse the cobalt platinum. And as I increase the pulse duration, at first, nothing changes much, but then at some point, this blue region starts to become white until it becomes completely white. And so this white color basically means that the overall magnetization is zero. And this is because I have a multi-domain state with random domains pointing up and down everywhere in this region. So the spin current not only allows the magnetization reversal, but it also prevents the formation of this multi-domain state. Another way to change the spin currents is by changing the amplitude of the magnetization of the gadolinium, which mostly generates this spin accumulation and then spin current. So in this case, with 27% of gadolinium, I have a threshold fluence for the reversal of the ferromagnet, which is 2.11 millijoule per centimeter squared. And now if I increase it by 6%, I see that the threshold fluence is reduced by around 22%. And in this case, because the concentration of the alloy here is so high, I don't have all optical switching of this layer, which means that I can reverse the magnetization of the ferromagnet without reversing the magnetization of the gadolinium iron cobalt. But this only works for one pulse, because then after the first pulse, when the cobalt platinum is switched, both magnetization of the gadolinium and the ferromagnet are parallel. And the reason why there is no reversal of the gadolinium iron cobalt required is because dm/dt is the highest during the demagnetization and not the reversal, and it's dm over dt which gives the spin current. So finally, I will present some time resolved measurements. So we use this setup with the first path where we send the pump beam with a certain incidence angle. And we have a second path here for the probe beam where we destroy the coherence of the light here with a chopper and some tape. And this is used to perform kerr microscopy. And so by changing the delay, we get different microscopy images. And this allows us to have the magnetization as a function of time and also as a function of fluence, because the spatial profile of the pump beam is Gaussian. And so we put a quarter wave plate here in the microscopy path in order to retrieve the magnetization of a single magnetic layer. So in particular, just the ferromagnetic layer. And we verify that we indeed measure magnetization and not some artifact by repeating the measurements for several quarter wave plate angles. So here are the results for the magnetization dynamics of the ferromagnet for different fluences. So at low fluences, I retrieve the usual ultra-fast demagnetization behavior. But then as the fluence is increased, I see that I start reversing the magnetization. And here for the highest fluence, we manage to reverse 20%. So reverse the magnetization and retrieve 20% of the magnetization amplitude after a few picoseconds. And so if I look at the case for the highest fluence and I zoom in the region of the reversal, I see that the magnetization crosses zero in less than a picosecond at around 400 femtoseconds. And this magnetization dynamics happens in 3 steps. So first we have the ultra-fast demagnetization, then we have reversal and a slower recovery. And then after 2 picoseconds, the magnetization barely changes. So in order to try to understand this and see why it makes sense, I made some calculations with light pulse absorption in multi-layers, 2 temperature model, this phenomenological spin accumulation that are used as an input for the theory of out of equilibrium magnetization dynamics of ferromagnets presented in this paper. And this is what I obtained. So in black, it is the magnetization of the ferromagnet as a function of time. And so I retrieve first the ultra-fast demagnetization, reversal, and almost linear recovery. And then after a while, I see that the magnetization is also barely evolving. So just as the experiments. And so we explain this second step here by the fact that the magnetization is not at equilibrium. So the equilibrium magnetization is plotted here in blue. And so it is given basically by the electronic temperature. So at around 2-3 picoseconds here, when the magnetization is almost equal to the equilibrium magnetization, it means that the magnetization is at equilibrium with the electrons. And so we conclude that here at around 2 picoseconds, the magnetization reaches equilibrium with the electronic system. So overall, I showed you that using femtosecond laser pulses, we can trigger an out of equilibrium state in magnetic systems, which allows much faster magnetization dynamics to happen. Because of the demagnetization, we generate ultra-short spin currents, which can be used to reverse the magnetization of ferromagnets in less than a picosecond. And then we can tune the spin currents by changing, for instance, the ferromagnetic alloy composition or the laser pulse duration. Finally, I would like to thank my coworkers and also my collaborators from Tohoku University and Eindhoven University of Technology. And I also would like to thank you very much for your attention.